Hi, my name is Junaid Malik and today I'll be introducing FastONN. So just a little intro about the library. So FastONN is a PyTorch based GPU enabled library that we can use for configuring and running ONNs with different operator sets. FastONN comes pre-packaged with numerous operator sets that you can use, but it also allows the flexibility of adding new operators which you might find more suiting to whatever problem that you're dealing with. In addition to these, we also include a variety of utility functions to make the experimentation easier. And the library is open source, so you can clone it from the GitHub repository with the given link. So the problem that we will now be going through in this tutorial is an image-to-image transformation problem. So we will be using very compact architectures to deal with this problem. The problem involves translating 4 unique images to 4 unique output images. So we expect the network to not only go from one face to another face, but also learn such translations for all the 4 different faces. First, we will be configuring a very simple CNN to deal with this problem. So our architecture will consist of 3 layers. The first layer will have 16 neurons, the second will have 32, and finally the last layer will have only a single neuron. We will first see how we configure such an architecture and train it. A simple CNN architecture. Then we will see how we can convert the CNN architecture to an ONN based architecture with a given operator set. We will again train this network, and finally we'll also see how we can convert the CNN layers to self-ONN layers and then compare the performances of the 3 variants. Okay, so we will now proceed to doing these steps in a Colab notebook. So as you can see, we have a Colab notebook session, and we have allocated a runtime with a GPU. We can start off by first cloning the repository for FastONN. Once the repository has been successfully cloned, we can proceed towards installing it using this command. Okay, so we now have the FastONN library installed successfully on this notebook. So the next step is to import the utilities and the packages that we will be using from this FastONN library. So first off, I'm just importing the FastONN library, and then from the utilities we will be importing some helper functions, which I will explain later. Also from the FastONN we will import the helper trainer class, which I will show later how we can use to quickly run experiments and plot their statistics. And then from FastONN also we can import this optier class, which basically is the counterpart for a convolutional layer in terms of ONNs. So this is a direct replacement for a convolutional layer in a CNN. We will wait for this to complete. The second step is to use the data set for the given problem. So built into this FastONN library there is this image transformation data set that you can use right away. So the way to use is just call this transformation dataset function. It is already imported when we used this import command. So once the dataset is imported, we can call it like this and then create a data loader out of this dataset. If you are already familiar with PyTorch, these steps would be quite familiar to you, as they are common in most of data loading pipelines in PyTorch. So we will just go ahead and plot the different images in the dataset. As you can see, so this is the problem that we will be dealing with. We have 4 input images, and we will be trying to train the network to learn to transform all these 4 images to these 4 images basically. So the first thing that we will do is to train a simple CNN for this problem with the architecture that I explained earlier in the slides. So we can just go ahead and instantiate a simple CNN like this. Again, this is quite standard PyTorch convention. So we have 3 convolution layers, each having 16, 32 and 1 neurons respectively, and then we have the max pooling and the upsampling in the first and second layer respectively. So this is quite a simple network, again just 3 layers. We can go ahead and instantiate the network. Then comes the trainer class. So we are shipping with FastONN library this trainer utility class that you can use not only with ONN but with any PyTorch model. It makes it quite easy for you to track statistics and makes the code easily reproducible and also easier to read and debug if you want to come back to it later on. So the trainer class is quite simple to instantiate. We provide it with the model that we want to be trained, the training data loader, validation and test data loaders. We don't have those for this problem as we are just trying to train the network, not validate or test it on a separate set. So we can just keep them empty. We provide a loss function, an optimizer that will be used for training. It could be any optimizer that ships with PyTorch, or any of the optimizers that you wrote yourself. For example, you just have to import it and you can use it right away here. So the next thing is the learning rate. We set it to 1 to the power minus 4 for our experiments, and then in the metrics you provide what metrics you want to be calculated and optimized. So when we say here PSNR, so here we give the name of the metric, PSNR of course, and then we provide a tuple. So the first part of the tuple is the function that would be used to calculate this metric, which is calc PSNR in this case. Again, this calc PSNR function is already imported from this wildcard import from the FastONN utils. So we provide it with the function that will be used to calculate this metric, and also our objective for this particular metric. So in this case, when we say max, the network will this trainer class will automatically keep track of the network state, which provides the best PSNR for all the different modes, training, validation and test. Of course, in this case it will only be the PSNR on the training set. Then we provide the name of the device. So we will be using the GPUs for this experiment. A reset function, this could be a function that you use to reset the parameters of the model. If you don't provide one, there is a generic function which works basically out of the box for most of the networks that you define using PyTorch, and PyTorch is standard modules. If you have something very customized, you can provide a function here which will be used to reset the model's parameters, and then simply the model name and the verbosity level, we set it to 2. So we will see for every epoch and every run the statistics which are being calculated on the runtime. So we can just go ahead and instantiate this CNN, the trainer CNN class, right? And now we are ready to train the model. Here you will see 3 lines. So in the first line we tell the trainer CNN object to train this network for 1000 epochs with the parameters that we provided. Once the training has been completed, it will automatically plot the stats, in this case the PSNR, and the loss is automatically calculated, and after that we call the save all method. So after this it will save the complete object in a separate file which you can load later on to resume training or plot the stats or load the best state of the model. We'll just go ahead now and train this network. So our network is now trained. As you can see, the output statistics from the training and also the plots with respect to the PSNR, the metric that we provided, and of course the loss function that was used. So we see here that the CNN gets to a maximum training PSNR of 22. We will now go ahead and convert the CNN model to an ONN and see if the results get better or not. So we'll just copy this model and I'll show you how we can convert this to an ONN. So before we go here, as you're already familiar by now with ONN, we need an operator set library where we define the operators that we will be using to configure the ONN. So by default, there are a number of operators that come with the FastONN library. I will just go ahead and use some of those to populate our operator set library. So we have the multiplication. So first I'm going through the nodal functions. So we have the multiplication function, the cubic function, sinusoid, exponential, sine, hyperbolic, the sinc function, as well as the chirp function. For activation, we can just stick to tangent hyperbolic for now, and for pooling we can just say summation. Now we have these three lists where we have our nodal activation and pool functions populated. Now to convert all these to an operator set library, we will just call a simple function. So we can simply write oplib and then use this helper function that we have, and we just pass the nodal, pool and activation functions that we will be using for this experiment. Now we have defined an operator set library that we will be using to configure our ONN. So now the main part where we convert the CNN that we used earlier to an ONN. So what we can do is comment out the convolution layer and also the tangent hyperbolic activation, because it is already a part of the operational layer, and we will replace this with an instance of the op_tier class that I introduced earlier. So it is instantiated quite similar to a CNN, where we pass in the number of input channels, the output channels, the kernel size that we will be using, and now we have to specify the operators that we will be using. So for this particular problem, image transformation, we know from the ONN papers that there are certain operators which work well. They have been found out using greedy iterative search over different operators. So we can just go ahead and use the operators mentioned in the ONN paper. You can also implement your own searching techniques, or there will be some searching methodologies proposed by us as well, which will be useful in searching for the optimal operators. So for now we can just use the operators that we get from the ONN paper. So for the first layer we will be using the operator set1, and then we need to pass the oplib that we populated earlier, and then the padding, similar to how we did it for the CNN. So again, we don't need the tangent hyperbolic because it is already included in op_tier. We will keep the max pooling layer and then convert this convolution layer again to an operational layer. For the second layer, we will be using the operator set with the index 6. By the way, you can also see these operator sets if you just print out the operator set library. So these are the different operator sets. So when we set the operator set 1 for the first layer, we were using the activation function, the tangent hyperbolic, the nodal function cubic, and the pooling function as summation. For the second layer, we set it to 3. We set it to 6, and at number 6 we have the sync function. Basically the sync function with tangent hyperbolic and the summation as pooling. And now we will just go ahead and also convert the last convolution layer to an operational layer as well. So basically that's how you convert a convolutional model, a CNN model, to an operational one. We can just go ahead and erase these lines so that it's easier to see the network architecture. Okay, so basically we have the 3 operational layers replacing the convolution layers, and we can name this model as the model ONN. Okay, so now we have our model ready, and now we can proceed as we did before in the case of CNN, just using the trainer utility class for training this network. So we have already gone through all these parameters of the trainer class, and we can just go ahead and start training the model. So we can see now that our ONN model is trained. We see the training curves as before, tracking the progression of PSNR and the loss over the number of epochs. We see that the maximum PSNR achieved by the network is significantly greater than the one achieved by the CNN. So in the case of a CNN, we had this 22 dBs, and in case of ONN, we see that this is increased by more than 10 or 11 dBs, so it's around 32.9. That was it for the ONN. Again, as before, we saved the trainer class object in the model ONN file so that we can load it later on if we need it. Now we will proceed towards using self-ONNs instead of ONNs. So in case of ONNs, we saw that there is a need to define this operator set library and then have the suitable operators for each layer defined before we train the ONN. In case of self-ONN, that need is alleviated by cooking the optimal nodal functions using Taylor series approximations. So the code for self-ONN is not public yet, but for the sake of this tutorial session, we will be importing it from our private repository. We can just go ahead and import the self-ONN layer. So basically, just as optair was an in-place replacement for the convolutional layer, similarly self-ONN layer can be used right away as a replacement for a convolutional or an operational layer. So now that we have imported the self-ONN layer, we can define the model. So what we can do is copy our CNN model again, and paste it here. Now in order to convert this to a self-ONN, we need to replace each of the layers with a self-ONN layer. And additionally, we have to provide one parameter, which is the order of approximation for the polynomials. So for this problem, we can just simply set it to 3 for all the layers. Alright, so now our self-ONN is configured. Again, as before, we will just use the trainer class to train this self-ONN network. We can see that Again, the training curves, as we saw before in case of ONNs and CNNs, we see that the SellONN reached a top PSNR of 28.7 in the given number of epochs. Again, this is substantially greater than CNN, which was 22, but we see here that in this case it's not as good as the ONN, because the ONN is using the best, already the most suitable set of operators for this kind of problem, and SellONN has that added complexity of cooking the best nodal function automatically. So that's why for this particular problem we see that the well-defined functions of ONNs are more suitable, but still we get a very respectable PSNR in case of SellONNs without the need of manually defining the operator set library and the operators for each layer. So now we have seen how we can train ONNs and SellONNs using the FastONN library. Just as an added exercise to basically see the difference between the outputs of these networks, we can go ahead and see the outputs of these networks. So for that we can again make use of the trainer class. So basically we will go ahead and define our data loader again so that it doesn't shuffle the images, and then using our trainer class objects we can generate the predictions for each type of the model that we use. So for CNN we can just do this, and the same steps for ONNs and SellONNs. So now we have generated the outputs from each of these models, the CNN, ONN and SellONN, and now we can plot these figures to visualize the outputs. So for this we can simply write a for loop, and the same steps for ONN and also the SellONN. So here we can visualize the outputs generated from each of the networks. As we can see, as we also saw from the PSNR values, the CNN results are not quite clear to see, although the silhouettes and the identity of the output images is clear. We can see that the fine details are not at all recovered properly. Even when the network has been trained for 1000 epochs, we see in ONNs that the result is quite close to the ground truth images. Even the small details, for example, the outline of the glasses here and also the eyes behind the glasses, they're quite visible, and we can see that most of the semantic information has been recovered almost exclusively. With SellONNs we also see that the results are of course quite better as compared to CNN, not as good as the ONN, but again quite respectable, considering that in case of SellONNs we didn't have the need to find the best operator. So just with a third order approximation of the nodal functions, we see that we get quite good results. So to conclude this tutorial, we have seen how straightforward it is now to convert any CNN architecture to an ONN or a SellONN one. You can find the list of operators that can be used with ONNs in our article, which details the implementation. It is available on archive. In addition, if you face any issues when working with the code, you are encouraged to raise those issues directly on GitHub so that others can also benefit from your experiences. It's recommended that you post some example code along with whatever error that you are facing, so that it is easier to reproduce and remedy the issue that you are facing. So when you're using the repository, please cite following papers: regarding the implementation and the general idea behind ONNs and self-ONNs. Now if you have any questions, I'll be happy to take them. Thank you.